Welcome back. Okay, so a quick recap on the alternator rectifier circuit. So on the end of our crankshaft we have our rotating magnetic field, which consists of a permanent magnet alternator or a electromagnet. In this case it's an electromagnet. It's got our two slip rings that our DC is passed via our carbon brushes housed within our stator. So our stator slips over the top of that. The conductors within our stator cut that magnetic field, inducing a voltage in the three wires. So remember, we had three wires connected in a star configuration, with our center tap being to the bike frame. That's our bike. Not really. Okay, so, and recall that our voltage coming out of our stator is alternating current, so that's passing current back both directions, AC. So that looks like that. Three of them, and they're not timed identical because they're displaced in our stator at a point where they don't pass the magnets all at exactly the same time, so there's a phase difference, a degree of difference between them. Now, in our home electrical system in Australia, it's 50 Hertz a second, so 50 cycles a second of that. On our motorcycle can be idling excuse me, so our crests of our voltage waveform can be spaced out quite a way. That's going to affect the voltage to our battery, or if we're blasting down the strip, we've got no lights on, or if we're blasting down the strip regardless of our lights being off or on, our crest of our voltage is going to be closer together, and depending whether our lights are on or off, what loads we're using will dictate how much voltage is getting to our battery. Of course, that's all controlled by our regulator rectifier, how much voltage gets to our battery, but of course it also depends on our load that we've got on our bike as well, as to how much is being put to ground by our regulator rectifier. If that's all a bit confusing, I'll break it up, try and explain it a little clearer as I go. Okay, so our this is a different bike. These two units are not off the same bike. So this would be our plug that would plug into here. See, this has 6 pins, this only has 5, but 3 of them are still our 3 phases at our plug there. The other 2 are our DC input via our carbon brushes. Sorry, graphite brushes they are, not carbon. And I think those are our DC, the 2 external ones there. It doesn't matter. 3 phases, 2 DC. The 6th one on this particular bike is our ground. If this were the stator to go with this pin and only had 5, the stator would be internally grounded, so it would be grounded to the frame of the bike. So getting back to that, our 3 phases, it does not matter which way these go round, just the same with our DC going in. All that's going to do, if we swap our DC going in, that's going to change the phase shift. It's going to change our magnets from a north to a south and a south to a north. That's just going to change our phase output. Our AC is just going to change slightly. They're just going to fire at different times. Again, if we shift our three phases round, then that's just going to swap our AC into our alternator regulator. We're still going to get that alternating waveform that I drew earlier in the other episode, but it's just going to change which one arrives first, which, as you'll see, does not make a difference at all. Alright, so what is in this little puppy here? First off, you'll notice that they have these ribs on them here. These are cooling ribs, so these things are designed to stick out in the wind. Don't lock them away. If you're customizing your bike, they need to breathe, they've got to stay cool. So housed within our unit here is what's known as a bridge rectifier. Now that is made up of diodes, and a diode is a little wee accessory, I guess, which only passes current in one direction. That's that band. Only passes the current in whichever way it's pointing. So you've got a little arrow here with a wall on one side, so the current can't go against the wall, it can only go with the arrow. So that's our symbol for our diode. I did have a diode here, it doesn't matter, gone. So our bridge rectifier is going to consist of 6 of these. Connected like this. That would be our DC. So our sine wave is coming along, our alternating current is going back and forth, back and forth. It's not connected like that, sorry, that's not there. Let's get rid of that, no point making this any more confusing than it needs to be. Right, so our AC wires from our plug are connected like, so, into the center of our bridge rectifier, tapped into the center. So that's our plugs there. They plug in like so. So we've got our AC, our alternating current, zipping along here into our center tap. So when it wants to go that way, this diode will pass half of our sine wave. So we'll get half of our sine wave zipping down there. And oops, I've drawn that wrong. So these ones, this will only get half of our sine wave will get passed that way. The other half of our current, which is going that way, can't go through there because it's blocked. So it doesn't go anywhere. In fact, that's a return path. So we've got no current coming this way, we've only got current going that way. Half sine waves, and that happens on all of them, bearing in mind that they're not firing all at the same time. So we've got these sine waves, half sine waves zipping down there, meeting up, end up something like that. So that's our direct current, but it's not a smooth DC, it's a pulsing DC, but our motorcycle doesn't care about that. So if we were to get our voltmeter and put it across our battery here, This is our charging circuit. It should be 13.5, 14 volts, something like that. If you were to measure these on AC, you can disconnect them while the bike's running. I think you'd find that it'd be about 17 volts. So 17 volts AC converts to about 14 volts DC. So that's our rectifying part of the regulator rectifier. So how do we test this? Well, get an ohm meter. I've changed meters here. I like this analog meter better. It puts out higher voltages than the digital one. Still only low, but higher. So we'd find our red and our green. Would be our red and our green. Start with the red. Go to ohm scale, and we put our other probe to our 3 phases. So essentially we're going from there to there. So our path is along our wires into our bridge rectifier. Depending on these meters, they push out voltage as well, a DC voltage. So depending on which way around you've got your probes, your current will pass that way, or it'll attempt to go back that way. So if you've got your current going in this direction, you'll go through this diode here back to your other probe. You can't go that way because it's blocked, so you'll measure your diode that way. Across your diode you should get no resistance. If you put it around the other way, you would. So we'll go on to our red wire across our 3 phases. So in that one direction, there's that bloody band again, we've got a low resistance, which is what we want, because we want in one direction, we don't want, there's that bloody band again, we don't want our current impeded. Whereas if we swap them round, give me 3 hands. Where is it? Where's our greenie? There it is. Is that what we got last time? No, we were on the red, weren't we, last time? So we're back on the red, so we've got an open circuit in that way. Trust me, I've tested it, it's an open circuit. Whereas we go to the green wire, to our pins, we'll be checking the current that way, through our pins, through our diodes. So green wire, do the same thing, check your other diodes in one direction. You'll have low resistance. In the other direction you'll have high resistance or open circuit. So that's what you're looking for. That's how you check the rectifier part of your regulator rectifier. I hope that made sense. Now the other part which you can't really test, you can but you can't, is our voltage dissipating circuit. So that puts any excess voltage to ground. So if you're blasting down the road, your sine waves are going for it, you're pumping out heaps of voltage, then we'll just call it a voltage gate. It's not what it's called, but we'll call it that because we don't need to call it anything else. That's attached to resistors. We'll call them resistors. Resistors are measured in watts, are rated in watts. Watts is a measurement of energy over time. So in this case it's heat. These resistors turn the energy into heat and they dissipate them. It dissipates the heat through our cooling fins, through our body of our bike. That's why we need to keep these out in the air, otherwise they cook. So they can get reasonably warm. So we've got heat coming off here, so our excess voltage is being bled to ground via our resistor, turning it into heat. So our voltage gate is looking for 13 volts. Anything over, it's going to send it to ground via our resistor. So we can check that. What we do is we just go across our battery. Maybe we put our bike at 3 grand and we just do a voltage check. This is not a voltage meter. We just check across our battery. We should get 13 volts. If we get higher, 15 volts, that's no good. That's going to cook our battery. Then for some reason our voltage sensing unit is not getting rid of it. If it's too low and you've proven everything up to this point, then you can just about bet that this unit has failed again as well. It's putting too much voltage to ground. For some reason that gate is permanently open. So you can't fix these, they're a sealed unit. You just have to toss it, replace it. Alright, I hope that was clearer than mud. Any questions, please shoot me an email. If you don't like the way I talk, abuse me. If you want to win one of my bikes, my latest bikes, check out winnercafracer.com. Like my video, go to my page, check out what else I do. Thanks for watching.